It looks like you have someone in the waiting room. Ah, you just admitted them.
Dear Professor William Phillips, dear colleagues and friends, dear participants, a very warm hello, everyone. I am very happy that this evening we have another wonderful episode of the inspiring online quantum science and technology seminar series of TÜBİTAK, Research Institute for Fundamental Sciences. We organize these seminars for national and international audiences with the participation of distinguished scientists and great speakers of the world, and rely on the unifying feature of science for humanity, which provide us with the power and wonder of shared ideas. We also organize these seminars to minimize the negative impacts of COVID-19 situation in the world on scientific thoughts and science-based actions. With this in mind, it is my sincere pleasure to welcome all of you for this very special event. Those of you joining us through the Zoom platform and those of you watching us through all social media platforms of TÜBİTAK, the Scientific and Technological Research Council of Turkey. I am also extremely happy that I have the privilege and honor of introducing our tonight's very, very special speaker, Nobel laureate, Professor William Daniel Phillips, world-renowned physicist, a world star of quantum science and technology from the Joint Quantum Institute, joint between the National Institute of Standards and Technology and the University of Maryland in the United States. Professor William Phillips indeed does not need any introduction. Nevertheless, I would like to make a brief introduction. He is a remarkable mind and scientific spirit, as gracious as he is brilliant. He has kindly agreed to join us for this seminar, and he is going to give a great talk, a new measure, the quantum reform of the metric system. Professor William Phillips is an American physicist who shared the Nobel Prize in Physics in 1997 for his contribution to laser cooling and technique to slow the movement of gaseous atoms in order to better study them at the National Institute of Standards and Technology, and especially for his invention of the Zeeman slower. One result of the development of laser cooling techniques was the first observation in 1995, the Bose-Einstein condensate, a new state of matter originally predicted 70 years earlier by Einstein and Indian physicist Bose. Professor William Phillips' research interests are laser cooling and trapping of neutral atoms, quantum information with single atom qubits, atomic gauge Bose-Einstein condensates, atoms in optical lattices, atomic physics analogs of condensed matter systems, coherent de Broglie wave atom optics, and collision of ultra-cold atoms. William Phillips graduated from Juniata College in 1970, summa cum laude, that is, with top honors. After that, he received his physics doctorate from Massachusetts Institute of Technology, MIT. And in 1978, he joined NIST, National Institute of Standards and Technology. Phillips has been awarded numerous honors, among them Michelson Medal of the Franklin Institute, election of the National Academy of Sciences, Nobel Prize in Physics, Golden Plate Award of the American Academy of Achievement, election to the European Academy of Arts, Sciences and Humanities, Presidential Rank Award, Service to America Award, Career Achievement, and many others. With this, I want to thank once again Professor William Phillips for joining us. Bill, we are extremely honored to host you for this seminar and look very forward for your talk. Please.
Thank you very much, Alikram. I'm going to try to share my screen now, and let's hope that all works well. Okay, can you see my my slide?
Yeah, it is okay. It's
Okay,
perfect.
wonderful, wonderful. Let me just okay. Great. Well, I'm going to be talking about a new measure, the quantum reform of the metric system. And as you've heard, I'm coming from the National Institute of Standards and Technology and the University of Maryland. We have a joint quantum institute. NIST is the National Metrology Institute of the United States, in the same way that the UME is the National Metrology Institute of Turkey. And it's a pleasure to be here with you. At NIST, I'm a member of the Laser Cooling and Trapping Group, and Gretchen Campbell, Paul Lett, Trey Porto, Ian Spielman, Ida Tietzinger, and Charles Clark are all members of that group, and it's a pleasure for me to work with them on a regular basis. Now, are you seeing my second slide now?
Yeah, it's okay.
It's okay. It shows NIST and IUPAP.
Yeah.
Okay,
exactly.
good. Well,
Exactly.
so it seems to be working. Okay, so in addition to representing NIST, I'm also representing the International Union of Pure and Applied Physics, which has been a key player in the establishment of the international system of units and of the reforms. And I'm giving this talk also as a representative of IUPAP. Now let's see, somehow or other that was the wrong slide. But before I go on, I also want to say how pleased I am that we're joined today by my good friend Bülent Atalay, who is a Turkish-American physicist. And in addition to being a physicist, he also has a wide range of interests and has a very famous book called, in English, Math and the Mona Lisa. And it's also available in Turkish, as well as a large number of other languages. And so if you want to read about art and science in an integrated way from a wonderful scientist and a wonderful artist, I highly recommend that book to you by Bülent Atalay. So let's go to the talk. So what has happened to the International System of Units? On the 20th of May, about 2 years ago, the 20th of May, 2019, the world has experienced the greatest revolution in measurement since the French Revolution. The French Revolution brought us the metric system. The French revolutionaries, as part of their revolutionary philosophy, wanted to have a system of measurement that was going to be good for all time and for all people. And this medal that you see here with this mythological creature, can you see my arrow pointing, Alakram? This mythological creature measuring the Earth is indicating the universality of the measurement system. Alakram, are you seeing my arrow?
Yeah, I see. Everything is okay with Raw. It is moving.
Wonderful. Wonderful. Thank you so much. So the new revolution that we're having, the French Revolution gave us the metric system, and now this new revolution is a change to the international system of units, the modern metric system. In French, the Système International d'Unité, so we abbreviate that as the SI. And the nature of the revolution is that all of the base units of the international system are now defined by fixing the values of constants of nature. Now, to understand how it is possible for this to be done and how an earlier unit of measure, namely time, has changed over time, and with apologies to the late, great Stephen Hawking, I'm going to bring you my version of a brief history of time. Since we have had seconds, the second has been 1 over 24 times 60 times 60 of 1 day. But since at least the beginning of the 20th century, we have understood by measuring it that the day is not constant. The tides slow down the rotation of the Earth. Earthquakes redistribute the mass of the Earth and change its rotational speed. And so we had a definition of the second, which was not itself constant. That is, because the rotation of the Earth is not constant, what a second was not constant either. Well, that was not a good situation for metrology. How did we know it? Because there were clocks that were better than the Earth. The first such clocks were mechanical clocks, but later people made atomic clocks. This is a picture of the first atomic clock. It was actually a molecular clock. It used ammonium at the National Bureau of Standards, the ancestor of my institution. In 1949, it was the first atomic clock, and it was much better than the rotation of the Earth. Later, at the Metrology Institute of the United Kingdom, they made a cesium clock in 1955. It was also much better than the rotation of the Earth. And so we now had a situation where the old metrology that involved the Earth was insufficient for the needs of time metrology. You can't very well use Earth rotation as a standard if you want to study the variation of the Earth's rotation. And so in 1960, when atomic timekeeping, a much better technology, was over a decade old, they redefined the second to be a fraction of the year 1900. What were they thinking? It's true that the year 1900 never changes, but it is not exactly readily available for measurement today. So finally, in 1967, the international body that makes such decisions redefined the second in terms of atomic transition frequencies. And the new definition was that the second is the duration of a certain number of cycles, about 9 billion periods of the radiation connecting to hyperfine levels in cesium. So this frequency of cesium, this constant of nature, became the definition, the new definition for the second. And atomic clocks kept getting better and better over time. But eventually, the best of those clocks stopped improving at an accuracy of about 10 to the minus 14. Now, 10 to the minus 14 is an incredible accuracy, but we are never satisfied in the metrology community. And the reason why the performance of clocks was stalled at 10 to the minus 14 was because the cesium atoms were moving so fast. As you heard in the introduction, some of my work has involved laser cooling, and that process of cooling cesium atoms down to temperatures below 1/1,000,000th of a degree above absolute zero improved the performance of these clocks, so that today, all over the world, we have atomic clocks like this one. This is called an atomic fountain because the cesium atoms are cooled down here. They're shot up in the vacuum. They fall back down again like a water jet. And these clocks are good to a few parts in 10 to the 16. This is the most accurately that any quantity in the International System of Units is measured. So what has happened is something very important. We started off with something quite arbitrary, the rotation of the Earth. The rotation of the Earth, there's nothing special about it. Nothing keeps it constant. It changes all the time. And that was replaced with something that does not change, namely the frequency of a quantum transition in an atom, in this case, in cesium. So that is a very important milestone in metrology. Now, I'm going to tell you another story, a short history of length. The original approach to length standards was to use the human body. A foot was a foot. The cubit was the distance between the elbow and the ends of the fingers. A fathom is the arm span. And this was really convenient because you had your standards with you, but it wasn't consistent. If you were buying fabric from a short fabric merchant, you might not get as much fabric as you wanted. Well, how to solve this? the ancient Egyptians, as well as many other ancient societies, solved this problem by assigning the body of a particular person, typically the monarch, in this case, the pharaoh, as the standard of length. And so the length of the pharaoh's forearm became the royal cubit. And it was enshrined in an artifact standard, a piece of stone that was carved to be the same length as the pharaoh's forearm. This became the standard of length for all of Egypt. Now, people who were out in the field building the pyramids had wooden standards that they had to calibrate every month against the stone standard to keep the standards reliable. And the penalty for not recalibrating every month was the death penalty. These people were really serious about their metrology. And as a result, they produced extremely good buildings. The pyramids have baselines that are consistent to a small fraction of a percent. They're square to 12 arc seconds. These are really well-made monuments because they were so serious about their metrology. Well, that principle of making artifacts was common throughout Europe in medieval times. They put standards into the walls of the town hall, in this case, in the city of Regensburg. The problem was that while this made it readily available to everyone in the town, if you went to a nearby town, there would be a different standard of measurement. Here in Bavaria, you can see, relative to this lovely tourist, the length of the fathom in Regensburg was quite long. So it was probably a good place to buy fabric. But if you went to some other town, you might get less fabric for the same measure. So what to do? Well, the French revolutionaries' approach was to create a standard of measurement that would be good, remember, for all time, for all people. And so they invented a new unit of measure that they called the meter. And the meter was to be 1/10 millionth of the distance from the North Pole of the Earth to the equator along a meridian passing through Paris. So how did they bring about this new definition of the meter? They sent out teams of surveyors north from Paris to Dunkirk and south from Paris to Barcelona in order to measure the length of this section of the meridian and then extrapolate it to the full length of the meridian. So they did that with this spirit in mind that this would be something available for everybody because everybody has access to the earth, that it would be good for all time because as far as they were concerned, the earth didn't change. Well, of course, as we know now, the earth does change, but they didn't know that. However, they realized, as did the ancient Egyptians, that it was not very convenient to use the earth as a standard. And so they did exactly what the ancient Egyptians did. They made an artifact. And this is a picture of a bar of platinum made to be equal to the length of the meter that had been determined by the surveyors who measured the distance between Dunkirk and Barcelona. And this was manufactured and then deposited into the archives of France. And in 1799, it became the standard of length for the country of France. A few years later, a few decades later, in 1875, there was an international treaty signed by 17 nations of the world. By the way, Turkey was one of those nations. It was at that time known as the Ottoman Empire. It was one of the original signers of the 1875 Treaty of the Meter. And part of that treaty specified that a new artifact standard would be made. That was called the International Prototype of the Meter. And this is a picture of one of those meter bars. And actual meter is defined to be the distance between two scratches, which were placed in that meter bar to be as close as possible to the length of the old meter of the archives from end to end. So we now had this new standard in the years following 1875. But almost as soon as that new standard was put into place, people realized there were better ways of measuring length. After all, these are scratches on a piece of metal. You look at the scratches with a microscope. Where is the center of the scratch? It may not be so easy to determine that to the level of precision that was possible using optical instruments. So this is a cartoon of a Michelson interferometer. The idea here is that you send light into this beam splitter, say a half-silvered mirror. Some of the light is reflected and goes to this mirror. Some is transmitted and goes to this mirror. Each mirror reflects the light back. The light recombines here and creates an interference pattern like the one that you see here. Now, the beauty of this interferometer is that if this mirror, the movable mirror, is displaced by just 1/4 of a wavelength, then this central spot of the interference pattern will change from being dark to being light. So that means that you can measure something less than 1/4 of a wavelength of light quite easily with this device. That is a fraction of 1/millionth of a meter, and you can't even see the details of the scratches on the meter bar with a resolution better than 1/millionth of a meter. And so people began to use light as a de facto standard. They would quote length measurements in terms of the wavelength of some kind of light. And so many decades later, in 1960, which was in fact the year that the laser was invented, or the laser was first operated, the meter was redefined to be a certain number of wavelengths of light coming from this krypton lamp. But soon people realized that lasers had gotten so good in the years after 1960 that laser light was much more pure than the light coming from this krypton lamp. And people started to use laser light as the de facto standard of length. And here's a picture of one of those lasers, an iodine stabilized helium neon laser. So the red light from a helium neon laser is sent into an iodine absorption cell. It has some iodine gas in it. And the resonance with those iodine molecules is used to lock this laser. And this became the unofficial standard of length used by people all over the world. But when they quoted length referenced to this standard, it wasn't the International System of Units. It wasn't the official standard of length, which was still based on the krypton lamp. And so it was clear that again, we faced the same situation that we have faced again and again historically, that we have a technology that can measure things better than the definition of the thing that we're trying to measure. We saw that with time, and we saw it in the past with length, and now again we're faced with that same situation, where the technology of the iodine stabilized helium neon laser is better than the technology of the krypton lamp. The obvious thing to do would have been to redefine the meter in terms of the wavelength of the iodine stabilized helium neon laser, but they did not do that. Instead, they made a truly brilliant and beautiful choice. They defined the speed of light. What does that mean? The new definition of the meter is that the meter is the length that light travels in a certain time interval, 1/299,792,458 of a second, okay? That is effectively defining the speed of light. We have this universal relationship that says that the wavelength times the frequency is equal to the speed of light. We've now defined the speed of light. It is possible to measure the frequency. In fact, it was the fact that we could measure the frequency of light that allowed this definition to be made. So if you take any light at all, the best laser you have, you measure its frequency, you take the defined value of the speed of light, just read off here, you know immediately what the wavelength is for any laser. And the beauty of this is that if someone makes a better laser, this still works. If someone devises a new way of measuring frequency, this still works. The definition of the meter is still good. And people did make all those advances. They did make better lasers. They did make better ways of measuring the frequency of light. And so we have an even better thing that happens. We started off with an artifact for length. We changed it to a constant of nature having to do with a particular atom. And then finally, we did something more universal. We defined the speed of light so that we were not tied to any particular atom, so that improvements could be incorporated without changing the definition. And so we should never need to change the definition of length again. All of the new technologies should be incorporated into that one final definition of length. And now, given that beautiful and brilliant definition of the meter, we want to bring that same beauty, that same brilliance to a redefinition of the kilogram. And for that matter, to the ampere, the Kelvin, and the mole, all of these 4 units of the International System of Units. Why was it necessary to do this, particularly for the kilogram? And how was it done? Well, for that, I'm going to give you a light history of mass. As has been true again and again, we began with mass standards that were artifacts. Here's a set of ancient Babylonian stones, polished stones, that formed the mass standards for that society. And all over the world, you had similar artifacts. Well, the French revolutionaries wanted to bring universality. And so they used their definition of the meter to define a new standard of mass, the kilogram. They said, take a cube, 1/10 of a meter on the side, and fill that cube with water. The mass of that water is equal to 1 kilogram. So the new definition was that a kilogram was the mass of 1 liter of water. That new definition, around the same time as the new definition based on the meter, sounded wonderful. Everybody can have access to water. The meter is the new length standard. But the problem was the density of water changes with temperature. Water sticks to things that you put it in contact with. It's hard to make a perfect cube of water. And so the French revolutionaries did what everyone has done again and again in these cases. They made an artifact. Here is a picture of that artifact. When I visited the archives of France, they allowed me to hold the case that holds what used to be the mass standard for all of France. This thing made in 1799, this platinum kilogram, that became the mass standard for all of France, just as artifacts have become the standards in so many cases. A few decades later, we had the International Treaty of the Meter. They agreed internationally that everyone would adopt this metric system, and they mandated the creation of a new artifact kilogram, which we call the International Prototype of the Kilogram, or the IPK, made of platinum iridium. You see it here, protected under 3 different glass jars. And this was the last artifact. Now think about this. This is now the 21st century. The unit of mass, up until 2 years ago, was an artifact, an actual piece of metal made in the 19th century based upon an object, the kilogram of the archives, that was made in the 18th century. That in the 21st century, we are still using 18th century technology is, in my opinion, scandalous. Think about this. If you were to leave a fingerprint on the International Prototype of the Kilogram, everyone in the world would lose weight. That's intolerable. Now, Nobody is leaving fingerprints on the international prototype of the kilogram, but it appears that its mass is changing nevertheless. Here is a plot of the mass of a number of copies of the kilogram, copies that were made at the same time that the international prototype kilogram was made. And every few decades, the mass of these objects is compared to the mass of the actual kilogram. And as you can see, almost every one of those copies is increasing in mass relative to the prototype kilogram. But when you see a plot like that, it makes you believe maybe the international prototype of the kilogram is the thing that is changing its mass, because all these other things are changing in the same direction. So maybe the international prototype of the kilogram is changing its mass, but by definition, it cannot change its mass because by law, it is always a kilogram, regardless of what happens to it. Well, this again is intolerable. We can't have a standard that changes. That's what we faced when we changed the definition of the second, a standard that was changing, but that was intolerable. And now we have a standard of mass rather than a standard of time that is changing. That is intolerable. How are we going to fix it? And the answer is we're going to fix it the same way we fixed the problem of the meter. We're going to define a constant of nature. For the meter, we defined the speed of light. What are we going to use for the kilogram? Well, to see that, let me remind you of what certainly must be the most famous equation in all of history. E equals mc squared, Einstein's famous equation that relates the energy of an object at rest to its mass times the square of the speed of light. So E equals mc squared. Now, a slightly less famous formula, but one that you probably know very well, is Planck's equation, or Einstein's equation, for the energy of a photon, a particle of light. That energy is equal to Planck's constant times the frequency of the light. Now, let's combine those two equations. We solve for the mass, and we find that the mass, and I'll say in a moment what that mass is equal to Planck's constant times the frequency divided by the square of the speed of light. Now, what mass am I talking about? Imagine I had a radioactive nucleus that emits a gamma ray. If I can measure the frequency of the gamma ray, which I can, and I know the speed of light because we've defined it, and if I also define Planck's constant, then I know how much that nucleus changes in mass when it emits that gamma ray. Now, it turns out, while we can make such measurements, they're not good enough for making a new mass standard. And so instead, we turn to this gentleman, Brian Kibble, who invented something called the Watt balance. We often call it the Kibble balance now. It's an electromechanical device that allows us to realize a new definition of mass based on defining Planck's constant. So let me show you how that works. Here is, now before I go on, I want to ask you, Alakram, can you see my cursor? Do you see anything moving on the screen?
Yes, that's okay. Perfect.
You can see me circling this right-hand side?
Yeah, exactly.
Wonderful, exactly. Wonderful, wonderful. Okay, so now I invite you to remember the traditional way of measuring mass. If I have an unknown mass on the right side of this balance, I weigh it, I determine its mass by putting standard masses on the other side of the balance until the balance balances. And when the balance is balanced, then that means that the unknown mass on the right side is equal to the sum of the standard masses on the left side. Now, I want to invite you to think of a different way of measuring mass. Let's imagine that we're going to balance the gravitational force of the unknown mass with an electromagnetic force. We're going to take a coil of wire, put current in the coil of wire, immerse that coil of wire into a magnetic field created by some permanent magnets. And if we can measure the current, if we know where the current goes in all the wires in this coil, if we can measure the magnetic field at every point along this wire, both its magnitude and its direction, then we can calculate what the electromagnetic force is. And we can, using our measurement of the local acceleration of gravity, we can determine what the mass is, because we've equated the gravitational force to the electromagnetic force, and then the acceleration of gravity changes the gravitational force into the gravitational mass, and we've measured it. The trouble is that all those things I said we would like to do, measure the current, measure the magnetic field, we cannot do well enough to make this a good way to measure mass. And here's where Kibble comes in. Kibble says, okay, we cannot measure those things. Let's measure something else that we can measure very well. So Kibble says, take the coil, and instead of putting current through it, now let's take the leads of that coil and connect them to a voltmeter. Now, when the coil moves, it's like a generator. It generates a voltage, which we can measure on this voltmeter. We can also measure the velocity at which the coil is moving, and we call this the velocity mode. And what Kibble realized was, and I'll explain why in a moment, what Kibble realized was that if you measure the velocity and if you measure the voltage, that gives you all the information that you need to determine the mass. Let's just look at this again. We're going to let the coil move. It generates a voltage. When we move it in the other direction, it generates a voltage in the opposite direction. We call this the velocity mode. Now, using exactly the same magnets, the permanent magnets here, so it makes exactly the same magnetic field as we had before, we do the first part of the experiment. That is, we put current through the coil to balance the gravitational force with this electromagnetic force. We call that the weighing mode. Okay? Now, why does this work? Because the mass that we're trying to determine times the acceleration of gravity, so these two things together are the force that we are seeing in the weighing mode, times the velocity that we measure in the velocity mode, is equal to the current that we had from the weighing mode times the voltage from the velocity mode. So on each side of this equation, we have one measurement from the weighing mode and one measurement from the velocity mode. Why do these two things have to be equal? Because on the left-hand side, we have mechanical power, force times velocity. On the right-hand side, we have electrical power, current times voltage. In any good system of units, these two things must be equal to each other. And that's why we can solve for the mass and see that the mass is equal to the current times the voltage divided by the acceleration of gravity times the velocity. Great. A new way of measuring mass. But wait a minute, you say, you told us this was going to have to do with Planck's constant. Why? Where is Planck's constant in all of this? And the answer is that we have quantum ways of measuring electrical quantities. The quantum Hall effect from Klaus von Klitzing allows us to measure resistance using a quantum effect. And the Josephson effect from Brian Josephson allows us to measure voltage using a quantum effect. If we were to use the old way of measuring electrical quantities, this whole thing wouldn't work. It all depends on these new quantum ways. Well, here's Brian Josephson, and Brian Josephson taught us that if we had a voltage across a Josephson junction, that there would be a certain frequency associated with that, and the ratio of the frequency to the voltage is 2e over h. What Klaus von Klitzing over here told us was that if we had a two-dimensional electron gas and put current through in one direction, it would generate a Hall voltage in the perpendicular direction, and the ratio of the voltage to the current would be given in ohms in terms of this quantity, h over e squared. So what we're going to do then is use this way of measuring voltage in terms of the Josephson effect and current by first measuring resistance in terms of the quantum Hall effect, then putting current through the resistor and measuring the voltage drop across the resistor using the Josephson effect. We'll combine those things to see that our voltage measurement is proportional to H over 2E from the Josephson effect, that the current, which is proportional to the voltage divided by the resistance, with the resistance being proportional to H over E squared and the voltage to H over 2E, means that the H's cancel out so that the current is proportional to the charge of the electron. So when we put all those things together, we find that the charge of the electron cancels out and the mass is proportional to Planck's constant, which is what I promised you in the first place. Balances using this principle can realize the kilogram to about 10 parts in a billion, to about a part in 10 to the 8th. And that is better than the changes that we are seeing in the kilogram due to, well, we don't really know what those changes are due to, so I'm just calling it dirt. We don't know why the kilogram is changing, or even whether it's changing, or whether all the other kilograms are changing, because we don't have any standard against which to measure them. Now we do, and it is better than the degree to which those other standards are changing. So we have succeeded in what we wanted to do, which was to make something that was a standard of mass that does not change with time. And here is a picture of some of the heroes who have done this at NIST. And these people are really serious about their metrology. They have tattooed the values of the fundamental constants that are associated with this new definition of the International System of Units on their forearm. So you have to really be serious about metrology in order to do that. Now, here's a beautiful thing. When you've defined Planck's constant, you are not constrained as to how you use that definition of Planck's constant in order to realize your new definition of mass. And here is a completely different way of getting a mass standard by using Planck's constant. Imagine an atom at rest in its ground state. Typically, this will be an atom of rubidium. You take laser light and shine it onto the atom. You know the frequency of the laser light, so you know the energy of the photon, and you tune it so that it will excite this atom to the excited state. That is, the atom will absorb the photon. It will absorb not only the energy of the photon, it will absorb the momentum of the photon, which is Planck's constant divided by the wavelength. So now the atom is in the excited state, as illustrated in this cartoon, that this ball goes from being black in the ground state to being red up here in the excited state. And because the atom absorbed the momentum of the photon, it's moving. And we can calculate its velocity because it's simply equal to the momentum of the photon, Planck's constant divided by lambda, divided by the mass of the atom. Let's solve for the mass. The mass is equal to Planck's constant divided by the velocity times the wavelength. We have defined Planck's constant. We measure the velocity using the Doppler shift. It can be done very carefully, very accurately. We measure the wavelength of the light we use. And all these things are, quote, easy. That is, if you're a good enough metrologist, you can get a good number for them. And when we do that, it tells us what the mass of the atom is in units of kilograms, of the new definition of the kilogram. Now, all we have to do is compare the mass of this rubidium atom to the mass of a silicon atom, and this is done to very high precision in ion traps. Then we make a perfect sphere of silicon. This sphere, made at the German National Metrology Institute, is the most spherical object ever made. And it's made of isotopically pure single crystal silicon, which means that when you measure its dimensions, you have essentially determined how many silicon atoms are in here. And because you know the mass of silicon in kilograms, you know the mass of this object. It becomes a new mass standard, not an artifact. It is definitely not an artifact. Anyone could make one who could make these measurements. So it's not anything like the international prototype of the kilogram. It is a new way of realizing the definition of the kilogram because you have defined Planck's constant. So all over the world, people have been measuring with silicon spheres and with Kibble balances. And before the definition became official, they were effectively measuring Planck's constant. After the definition became official, Planck's constant was defined to be the best value based on all of these measurements together. And when their measurements of Planck's constant all agreed to a sufficient level of accuracy, the redefinition was made. And then on May 20th, the definition went into effect. What was the dream of the French revolutionaries, that we should have something that would be good for all time and for all people, by having this new definition of the mass based on Planck's constant. Well, there's one final part of the story, and that is the definition of the ampere has been changed, along with, as you'll see, two other units of the International System of Units. In the old days, which means more than 2 years ago, the definition of the ampere was that the ampere is the current which, when put into two long, straight wires 1 meter apart, would produce a force of 2 times 10 to the minus 7 newtons per meter. You may remember that from your physics classes about electricity and magnetism. What this definition of the ampere is doing, in effect, is defining what the quantity mu naught is. Mu naught is the magnetic permeability of the vacuum. This definition of the ampere defines that mu naught is equal to 4 pi times 10 to the minus 7 newtons per ampere squared. That was the old definition. Now, the new definition is that we have defined the charge on the electron. And because a coulomb per second is an ampere, defining what the charge of an electron is in coulombs tells you how many electrons per second you need in order to make 1 ampere. So that is the new definition of the ampere, is that the ampere is a certain number of electrons per second, because we have now defined the charge of the electron to be a certain number. What that means is that this old definition of the ampere is gone, and the idea that the permeability of the vacuum is 4 pi times 10 to the minus 7 is also gone. So if you have been teaching your students that mu naught is 4 pi times 10 to the minus 7, you must go to them and apologize, because it is no longer 4 pi times 10 to the minus 7. Now, unless you are making measurements at the level of a part in 10 to the 8th, you will never be able to tell the difference, because, of course, these redefinitions were made in such a way as to preserve the continuity of all measurements. But we have now changed that in our system of units. It also means that we've changed epsilon naught. Epsilon naught used to be a fixed defined number because the speed of light was defined and mu naught was defined. That meant that epsilon naught, the electric permittivity of the vacuum, was defined. That is no longer true. But the relationship between mu naught and epsilon naught stays the same because the speed of light is defined. Now, one of the beautiful things about having Planck's constant h, as well as the charge of the electron E defined, is that it means that 2e over h, the Josephson constant, and h over e squared, the von Klitzing constant, are now exact. So the constants that we rely upon in order to make electrical measurements are both exact. And so this is a wonderful situation. Two more things. The mole. It used to be, that is 2 years ago, that the mole was the amount of substance such that the number of elementary entities in that substance was equal to the number of carbon-12 atoms in 12 grams of carbon-12. And that number is what is known as Avogadro's number or Avogadro's constant. Today, Avogadro's number is just a defined number. So we've defined the Avogadro constant, and that becomes the new mole. And finally, the Kelvin, the unit of temperature. It used to be that it was 1 over 273.16 of the triple point of water. It is no longer. Now we define the Boltzmann constant. Now, what does that do? I love this because it makes the definition so atomic, so quantum. When we define the Boltzmann constant, then the thermal energy of the constituents of anything that whose temperature is being measured, let's say a gas, the thermal energy of that gas is Boltzmann's constant times the temperature. So we're defining temperature in terms of the energy of the microscopic constituents of the substance. This will, I hope, lead to better ways of measuring temperature by, for example, measuring the velocity distribution of atoms in a gas. Today, temperature is still being measured in the same way using ideal gas thermometers, but based on the idea that Boltzmann's constant is defined. And when you've defined Avogadro's constant, it means that you've defined the ideal gas constant as well. So the French Revolution brought us the metric system. Meters were used for length, kilograms were used for mass. The Convention du Mètre brought us an international agreement such that the whole world that represented were represented at that treaty signing, like the Ottoman Empire, Turkey, and the United States, and the United Kingdom, and countries like Brazil and Canada, were all signers of this treaty of 1875, and more countries have signed it, so that today 60 countries around the world are members of the International Meter Convention. And now we have the entire world using the metric system. And on the 20th of May, 2 years ago, which is, by the way, the anniversary, the 20th of May is the anniversary of the signing of the 1875 Convention du Mètre, we had the biggest change in the metric system since the French Revolution brought it into being. And that change is that every one of these base units of the international system of units is defined by fixing a value of the constant of nature. The kilogram by fixing H, the meter by fixing C, the second by fixing the hyperfine frequency of cesium, the ampere by fixing the charge of the electron, and so on. And so it appears that we have finally realized the dream of the French revolutionaries to produce a system that was good for all time and for all people. And when all of the requirements for measurements had been satisfied, so that the definition could be changed. In France, in Versailles, in 2018, the General Conference on Weights and Measures met to have a vote of all of the countries, the 60 countries, to vote whether this change should take place. And all 60 countries voted unanimously that they would change the definition. And this is the...
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community.
At times, it seemed
impossible.
Accurate.
Precise measurements.
Anytime.
Anywhere. But we did it.
Ce l'abbiamo fatta. We have nice geschafft.
L'holograms.
Wees je bully.
Biz buna nail olduk.
Proud om die.
We zullen het. Het is ons gelukt.
We сделали это.
Vi gjorde det.
Mi smo to učinili.
Dokázali jsme to.
Congratulations.
축하합니다. Felicitaciones.
Mazal tov.
Congratulazioni.
Șatere lăvărișa.
Selamat sukses.
Parabéns.
Ongela.
Omedeto.
Onneksi olkoon.
Mabruk.
Aiko.
Felicitations. Congratulations.
So when I see that movie, I still get emotional because the idea that 60 countries in the world would unanimously agree on anything makes me feel a greater degree of hope that perhaps the countries of the world can agree on other things as well. But at least now we have agreed on this new formulation of the International System of Units. Finally realizing the dream to create a system that would be good for all time and for all people. But it seems that we're there except for time itself, which is still tied to a specific atom, namely cesium, rather than to a fundamental constant. And already we have other atoms with different quantum transitions that allow the measurement of time better than is possible with cesium. And so the future of the definition of the second has yet to be determined, and only time will tell how we will redefine the second. But for now, we have come to the end, but it's not really the end because we still need to redefine the international second, and I don't yet know what that will be. Thank you very much.
Thank you very much, you, for this very exciting and comprehensive talk.
It's been a pleasure.
So now we can pass to questions. Please ask questions. You can still send us by email or using chat button your questions. Bill has kindly suggested that you may send questions in Turkish, and I can translate into English. I can do this. Please send question in Turkish if it is needed. This is a courtesy of Bill. We can accept questions in Turkish as well. I will translate into English.
But it's only because of you that I'm able to accept questions in Turkish.
So we have received several questions by email, and Bill, if you allow, I can ask you these questions. Can I ask you these questions?
Please. Yes.
So the first question is, as Einstein's special relativity teaches us, time has to be considered as the same footing with the space. This indeed follows from the fact that the speed of light in vacuum is a universal constant of nature. This in turn defines a flat four-dimensional metric, which is a measure of space-time interval between two events. In the new revolutionary metric system, as you nicely described, the time is still supposed to be linked to a specific atom. Indeed, you at the end yourself said about it. But the base units are defined by fixing the values of constants of nature, in particular the speed of light. But it seems that this is not the end of story. The time still needs to be redefined. Will you please elaborate a little bit more on this, in particular in the context of special relativity?
Yeah. Okay. So there's a number of important ideas in this wonderful question. One is that time is defined in terms of a specific atom, and this seems still a little bit antique. It's not the modern way of doing things. From a philosophical point of view, we would rather use a universal constant, like the Rydberg constant. The trouble is that we do not know how to go from the Rydberg constant to calculating the frequency of any transition as well as we can measure them. So that means that defining something in terms of the Rydberg constant would not be a useful thing to do. So we are still stuck with the idea of a specific atom. We will change what that atom is, but we're still stuck with that. So that's one thing. Now, let's talk about relativity. It turns out that the real issue is not just special relativity, but also general relativity. Because general relativity tells us that the clock frequency is going to depend upon where you are in the gravitational potential. And since we live in a gravity field, we cannot ignore the fact that there is, in fact, a gravitational field. So the idea of a space as imagined in the special theory of relativity is not reality. A clock at sea level, which is close to where I am now, will not keep time at the same rate as an identical clock in Boulder, Colorado, where the best clocks are. That will be off by more than a part in 10 to the 13. And these clocks, the best clocks today, can keep time to a part in 10 to the 18. So we're faced with a problem of reconciling time in different places because of the different gravitational potential. And we cannot, in fact, translate time in Boulder, Colorado to time in Washington, D.C. with sufficient accuracy because we don't know the gravitational potential well enough. Now, this does not mean that it cannot be done in the future. It's just that we need to learn more about the gravitational potential. In fact, people are now developing clocks to study the gravitational potential, to use it for measuring the Earth's structure. These are being used for geodesy, for example, for prospecting for minerals, or at least people are starting to develop these instruments for this purpose. So relativity comes in, but it turns out that general relativity is just as important as special relativity in this business. So that was a great question. Lots of interesting pieces to it.
Okay, thank you. The next question is, the new metric system is, of course, very profound, but on the other hand, it looks much more complex than the early existing one.
Yeah.
How will the reform of the metric system affect measurements and calibrations in everyday life? In the everyday life.
Okay, so for everyday life, it probably won't change things at all. Because when you're buying something at the store by weight, let's say you go to the store and you buy apples by weight, you don't need to know what the weight of those apples is to a part in 10 to the 8th. And the redefinition has kept everything constant within the experimental uncertainties. So that means that the new SI kilogram is the same as the old SI kilogram to within about a part in 10 to the 8th. So it doesn't matter for everyday life. But for some things, for people who really need to know what things are extremely accurately, it makes a difference. Also, it turns out, as a bonus, as an extra benefit of the redefinition, small masses will be easier to measure. You lose a great deal of accuracy going from a kilogram to a milligram. And I can talk about why that is and why we don't have that same problem with the new definition. But that's one of the great benefits is that small masses are going to be easier to measure. Now let's see. Did I answer all the pieces of that question? Oh, the fact that it's complex. it is true that it's more complex to have a Kibble balance than it is to have a kilogram comparator. But the fact is, both of these things are pretty expensive devices. So only the big metrology laboratories had kilogram comparators before, and only the big metrology laboratories will have Kibble balances now. So that won't be that different. And so if you are a secondary standards laboratory, you will send your mass standard to be calibrated against the National Metrology Institute, and they will calibrate it against the best methods that they have, just as before. But just as before, there will be a few places like the International Bureau of Weights and Measures, like the UME, like the NPL, like the PTB, where the primary standards are being realized. Now, there's one more point that is implied by this question. Because of the greater complexity of the definition, how do you teach students what a meter is? How do you teach students what a kilogram is? This, I think, is a real challenge. And I don't think we have come up yet with a good way of describing to students what a kilogram is using the new definition.
Yeah, thank you. Indeed, the next question also implied this final part of your answer, which says that what do you see as the main challenges to the future of quantum research and quantum education?
Well, this, I guess, is part of quantum education, as I've said, and I do think that this is a challenge to describe why this quantum way of doing things is telling us what mass is. Now, that second way that I did of describing how we could realize the new definition of the kilogram using the silicon sphere is perhaps a little bit more physical. We measure the mass of an atom, and then we count the atoms, and this gives us a new mass standard. But the process is still complicated, as opposed to saying the kilogram is the mass of a liter of water. That's pretty easy. I think that this is an important challenge that everyone who's interested in education can contribute to. But that's, of course, not all there is in quantum education. I think that right now, in our world today, we are seeing a tremendous increase in quantum technology. So it's not just scientific technology, but that scientific technology is becoming more and more quantum. So that we find at the Joint Quantum Institute that more and more companies are coming to us and saying to us, we need more people who have been trained as quantum scientists. Please produce more quantum scientists. And of course, universities can't immediately turn a valve and pour out quantum scientists. We have to train them over a long period of time. And we have to encourage more young people to go into quantum science. So I think that one of the challenges that we have is particularly to improve the participation of underrepresented groups in our society, to enter the study of science. Because if we're not using our entire society as a resource for people to go into the important areas that need to be staffed, then we won't be getting the best people in those areas. So I think that one of the challenges we have is convince people of all genders and races that quantum science is a good thing to study, and not just business and law where they can make a lot of money.
Thank you very much. It's a great answer. Thank you very much. So then the next question indeed continues this line of thoughts. What is your forecast for quantum science and metrology in the next decades? For instance, in the framework of measuring higher and higher transition frequencies.
Okay, well, so that particular one is something that I'm probably not going to be personally involved in, but I know a lot of the people who are. So, for example, we spent many decades learning how to measure microwave frequencies better and better because we needed to do that to realize the definition of the second using the cesium clock, because the cesium transition frequency was a microwave frequency. And microwave technology was already something that was reasonably well developed in the 1960s because microwave technology had been developed during World War II for radar and things like that. And so when that became mature and we needed to go to higher frequencies, then we needed to develop that same kind of expertise to measure optical frequencies. And there has been a tremendous historical development in being able to measure optical frequencies. And that continues to higher and higher frequencies. When I was beginning graduate school, people were measuring infrared frequencies directly. Using point contact diodes. And now people measure optical visible frequencies and even ultraviolet frequencies. The next frontier seems to be pushing this into the far ultraviolet. One of the reasons why this is of particular interest is that there is a transition in a particular radioactive nucleus that's at very low energies, so that it is something that we can probably make coherent laser light in the far UV to excite a nucleus. No one's done it yet, but we're working very hard on it. When I say we, I mean the community. I'm not doing it myself. And making those frequency measurements is going to be really important. And there are new techniques for using high harmonic generation, where you use say an atomic gas as a highly nonlinear medium to make high harmonics of a laser frequency. So all these things are being worked on together toward the idea of getting higher and higher frequencies. So it's really an exciting and adventurous time in this business of metrology. But that's only one feature of quantum metrology. For example, using quantum advantage to measure all kinds of things. Right now, the gravity wave observatories are operating, I would say, for the first time, making real measurements that people are really interested in, using squeezed light, using something that is non-classical quantum advantage. So the light being used in LIGO, for example, allows you to have a 3 dB gain in the signal-to-noise ratio, which is a big change in the volume of the universe from which you can see signals. So this really increases the efficiency of the gravity wave astronomy that you can do. And this is because of quantum metrology, beating the standard quantum limit as set by the uncertainty principle. So you don't really beat the uncertainty principle, but you choose where you want to take your uncertainty. And with LIGO, you can choose to take your uncertainty in the length of the interferometer arm, and not in, say, and give up the good uncertainty in the, say, the intensity of the light, so that you get a better uncertainty in the phase. So this, I think, is the first real example of doing this, and I expect this to propagate through a lot of measurement, where we're going to use things that give us quantum advantage.
Thank you very much. Wonderful, a wonderful answer. We have still a few questions. Can I ask you?
Yes, certainly.
Yeah, no problem. Okay, thank you. Thank you. This question seems to be a little lies aside of the general topics. Nevertheless, question I would like to ask you this question, which asks indeed Professor Attila Ashkar, Professor and President Emeritus of Koç University in Istanbul. The question says, Schrödinger equation has no dissipation and has been quite successful so far. Several phenomena such as interaction with unisolated systems as well as resonances where theoretical amplitudes that would become singular may need a dissipation. Do you foresee a need for accounting for dissipation in less common situations?
Yes, absolutely. In fact, I would say that Professor Ashkar has put his finger on one of the most important and exciting directions of quantum information science these days. So open quantum systems are significantly more difficult to treat theoretically than unitary closed quantum systems. So I'm thinking of the kind of open quantum system where we trace over the environment, but we still have that effect on the quantum system of interest. But just how these systems work in detail has become a really interesting problem in quantum information, because in order to properly treat the environment, it's often an intractable computational problem. So one of the things that modern quantum measurement science has told us is that a way of understanding how a quantum system undergoes dissipation is to think in detail about the quantum nature of the system to which it's coupled. But typically this is a big system and it's hard to deal with it because of the exponentially growing difficulty of dealing with a quantum problem as you increase the size of the system. Well, this is what quantum information, either quantum computing or quantum simulation, has a chance to address. So I think that these kinds of problems are an important part of what quantum computation and quantum simulation are going to do, is to deal with open quantum systems. So this is absolutely one of our favorite subjects to think about, and I expect really new kinds of results for these systems within the next few years.
Thank you. Can you please elaborate on the idea of a time crystal and its possible role in modern metrology?
Well, I don't know very much about time crystals. I know that the original proposition for a time crystal, so the idea of a time crystal is that you have a physical system that spontaneously creates a physical process that is periodic in time with a specific phase that represents a kind of symmetry breaking analogous to what happens when you have the spontaneous formation of a crystal, where things are periodic in space with a particular position of where the atoms are. This is often called symmetry breaking in condensed matter physics. So the idea is that a similar symmetry breaking, a term I'm not that fond of myself, that a similar kind of symmetry breaking could happen in the time domain and create some periodic feature. Well, it turns out that the original proposal for doing this, I think it was Frank Wilczek who came up with the original proposal. It turns out that there's a proof that you can't have that. So people then modified the idea of what they wanted a time crystal to be to include a driven system. So now you've imposed on the system a time periodicity. But the idea is that the system responds with a different periodicity that's related to the periodicity that you've imposed. So, for example, you might drive a system with a certain period, and then it would create some phenomena that happens with twice that period. And people call these things time crystals as well. And they're certainly interesting features, but it's not what was originally imagined. And there may be metrological advantages for that sort of thing, but I don't immediately know of any. So I think that they're more of a curiosity, a very interesting one. I think that they teach us a lot about nonlinear systems and about chaotic responses to periodic driving, but I don't know that there's a metrology application. At least I don't know of one. I'll be happy if somebody would tell me.
Thank you. The next question is about kilowatt balance. Does everyone indeed need a kilowatt balance now? Is it necessary or important today?
Yeah, so I would say it's only necessary for people who want to measure mass at the level of parts in 10 to the eighth. Then you need to have either a Kibble balance or you need to use this silicon sphere method. So if you don't need to measure mass at that level and need to have stability from year to year at that level, then you don't need a Kibble balance. It'll be perfectly fine for you to send your own physical mass standard someplace to have it calibrated. And if you have a platinum kilogram, not that many people do, then you can know what that is to parts in 10 to the eighth, and it'll stay that way probably for a few years at least. But if you need something better than that, then you'll have to have your own Kibble balance or your own other way of doing it with, say, a silicon sphere. If you want to measure very small masses very accurately, you might want a Kibble balance, but it won't have to be good to a part in 10 to the eighth, because normally people don't measure milligram masses to a part in 10 to the eighth. So your Kibble balance design won't be as demanding in terms of its fractional accuracy if you want to measure milligrams or anything smaller than a gram. You may want to use a Kibble balance just because it's better than traditional weighing.
Thank you. We have still another question, which says, why geometrical units are not adopted where everything is expressed in terms of the lengths when setting C, H, and G is gravitational constant, is equal to 1?
Yeah. Well, you could do that in principle. In fact, if I was going to have a system of units that was based on a single unit, I think I would choose time rather than length. But again, it's a matter of choice. The reason I think of time is that we're already used to thinking about lengths in terms of time. If you ask, how far away is the university? People will often say, oh, it's a half an hour away. Of course, what they mean is that you would drive there in a half an hour. But if we say, how far away is the nearest star? People will say, well, it's 4 light years away, meaning it takes light 4 years to get there. So it's something we're already pretty familiar with. And in this case, a nanosecond would be about 30 centimeters. So it's a convenient length. And everything else could work that way too. Energy could be in terms of inverse seconds, with the assumption that Planck's constant is equal to 1. So we could, and of course, once you've done that, then obviously mass is just energy. But think about this. it wouldn't be very convenient. If someone says to you, how much does that that bolt that you're going to put onto your spacecraft weigh? And you said that, well, it's, and I don't even know what the number would be, 10 to the 40th or 50th hertz. Well, that it might not be so easy to understand what that means. You would eventually get used to it. But the point is that our system of units is based on convenience. Our particular choice of units is based on convenience. We don't have our standard of mass be something that is 1,000,000 kilograms, and we don't have it be a nanogram either, because that's not the kinds of masses that we deal with on a day-to-day basis. So our standard of mass is something that is sort of human. In the same way, the meter is something that's human. The second, we've chosen the second, and it's sort of human. It's sort of like, the blink of an eye. So I think that these units that we have, the Kelvin, well, that's about the temperature difference that you can feel, right? So it seems that the human part of the measurement system has determined what it will be, but it is totally arbitrary. And it's that arbitrariness that made it necessary for us to define things in terms of fundamental constants. Because the things are totally arbitrary, if, imagine that we wanted to communicate with some alien civilization that was in some other star, and we wanted to tell them what we were like and what a meter is like, we could do that now. But in 1875, there wouldn't have been any way of telling them what a meter was if they couldn't see the Earth, or they couldn't, we couldn't tell them how long the meter bar was, because what would we use as a reference? But these new ways, we could tell anyone what our units are. But that emphasizes the arbitrary nature of these units.
Thank you very much. So final questions, please. Of the recent breakthroughs in quantum science and metrology, which excites you most?
Well, well, that's hard to say, because of course I'm excited by so many of the things that are going on. But asking which one excites me the most is sort of like asking a parent, which of your children do you love the most? No one could answer a question like that. But I'm really excited about the simulation of condensed matter problems using atoms and optical lattices. I'm excited about optical frequency standards and the ways in which they depend upon quantum statistics and the quantum nature of interaction between atoms. I'm excited about the creation of qubits and of quantum error correction applied to those qubits, something that's really just in its infancy. I'm excited about the possibility of making quantum computations that can't be made by classical computers. I'm excited by that thing that I already mentioned about the fact that LIGO is using a squeezed light to get a quantum advantage for the observation of more and more distant events. I mean, think about LIGO. Almost everything that they see is a new revelation. The idea that neutron stars and black holes are colliding and forming heavy elements that people used to think were only formed in supernova. It's just amazing what's going on. And quantum physics is part of so many of these things. It's just a really exciting time to be a quantum physicist.
Thank you. Bill, will you please make your final comments or remarks, and then we can close session if you don't mind.
Well, it's been a pleasure to be with you today, and I have particularly been pleased with the really insightful questions that all of you have asked. It's really wonderful to see people thinking so deeply about these issues, and so I just hope that you will continue to be part of this wonderful adventure, not just the adventure of science, but the adventure of quantum science, which is that is getting to be more and more attractive as time goes on. That you will continue to engage with this really exciting feature of the world that we live in.
Thank you very much. Thank you for this seminar, for coming and joining us. We will hope strongly that we will meet in person in future when pandemic will disappear from the world.
I certainly hope so, and I'm particularly hoping that my friend Bülent Adile and I can visit Turkey together, and that we can both give talks in person.
Exactly. We will be very happy to receive both of you here. Thank you again so much.